Hello there, and a very warm, soft welcome to the Calm Fact channel. Tonight, we are going to embark on a journey. It is not a journey that requires you to move, or to think, or to worry. It is a journey of the mind, a gentle exploration into the endlessly fascinating and wonderfully diverse world of eyes. Take a moment to settle in. Let your shoulders drop. Let your jaw unclench. These tiny, luminous gateways that we call eyes are the very place where your mind meets the world. They are the bridge between the internal universe of your thoughts and the external universe of stars and trees and light. Even in stillness, even when you are doing nothing at all, eyes shimmer with mystery. They are capable of picking up the faint, ancient light from distant stars that has traveled for millions of years just to reach you. They catch the tiniest of movements in the grass. They weave all of these signals into the continuous, flowing story that you call your reality. Every single glance you take holds a universe of intricate lenses and biological mechanics. Every blink you make resets the world, washing it clean, and every beautiful moment of sight you experience is built upon millions and millions of years of quiet, steady evolution. If you enjoy these quiet journeys into the wonders of our reality, I invite you to like, subscribe, or perhaps share a gentle thought below. It helps others find their way to this safe harbor too, one sleepy soul at a time. But for now, there is nothing you need to do. There are no obligations. All you need to do is relax. Let your body soften, melting into the surface beneath you. Allow yourself to drift, like a leaf on a slow-moving river, into the wonderful, silent world of eyes. Let's begin. Let us imagine the warm, dry air of a desert. Here, resting upon a heated stone, some lizards possess a secret hidden beneath their skin. High on the heads of certain reptiles, there lies a small, specialized light-sensing organ known as a parietal eye. It is a third eye, though it does not look like the eyes you and I are familiar with. It does not form clear images or pictures of the landscape. Instead, it is a dedicated guardian of light. It detects the subtle changes in brightness, the shifting of shadows, helping the creature regulate its daily rhythms and its seasonal behaviors. In many species, this parietal eye is covered by a thin, protective layer of skin or scales. This layer softens the incoming light, diffusing it like a paper lantern. Yet, beneath that skin, the internal structure remains complex. It includes a lens, a rudimentary retina, and a nerve connection that travels deep into areas of the brain involved in biological timing. This ancient organ offers us whispering clues about the very early evolution of vision. It is a window into the past. It may help the lizard sense the shadow of an overhead predator, or perhaps align itself perfectly with the sun for efficient basking, soaking in the warmth. It helps maintain the stable, comforting cycles of rest and activity. Although recent evolution has reduced its prominence in many lineages, its presence remains a gentle reminder that eyes come in diverse forms, shaped by the specific needs of different environments. While hidden from ordinary view, the parietal eye quietly contributes to the survival of creatures that rely on light in ways far removed from our human experience. It is a silent observer, watching the sky, keeping time with the sun. Now, let your mind float upward, into the open sky. Some birds can track movements faster than the human brain can even begin to comprehend. Raptors, the eagles, the hawks, the falcons, and other aerial specialists must react in fractions of a heartbeat. They must catch prey or navigate through complex, shifting terrain at incredible speeds. Their visual systems are tuned not only for sharpness, but for something called temporal resolution. This is the ability to separate rapidly changing images into distinct, clear moments. Imagine watching a film. To us, the frames blend together, but to these birds, their eyes feed information to brain circuits that process motion at a rate far beyond our capacity. This allows them to follow the precise trajectory of a darting animal, or to adjust their flight path during a high-velocity dive. To a person, that same movement might appear as a mere blur, a streak of color, but to the bird, it unfolds as a series of clear, crisp positions. Each position informs the next adjustment of a wing, the slight twist of a tail feather. Some species even have specialized regions in the retina, with exceptionally high densities of cells dedicated solely to tracking motion against the horizon. In the open sky, where distances are great and errors are costly, this speed of perception can make the difference between a successful hunt and a dangerous collision. It is a vision of the world that is faster, sharper, and more immediate than we can imagine. Drifting down from the sky, we land in a garden. But this is not the garden you see. Some animals can see ultraviolet patterns on flowers and feathers, patterns that are invisible to us. Bees, many birds, and several other species possess photoreceptors that respond to wavelengths beyond the human visible spectrum. To them, an ordinary flower, which might look simple and yellow to us, may appear adorned with intricate, guiding patterns. These hidden maps direct pollinators toward the nectar, like landing lights on a runway. Feathers that look uniformly colored to human eyes may shine with hidden contrasts to a bird. These secret signals help individuals recognize potential mates or identify rivals. The ability to see ultraviolet light transforms the landscape into a much more informative world, filled with signals designed through eons of evolution to attract attention. These patterns may highlight safe landing zones, identify specific species, or even warn of toxicity. Ultraviolet sensitivity also assists with navigation, since certain atmospheric conditions produce sky patterns visible only at these wavelengths. For creatures that rely on ultraviolet light, these cues are as familiar as the colors blue or green are to us. They shape daily behavior through channels invisible to most observers. Their visual universe stretches beyond human imagination, a secret layer of reality painted in colors we cannot name. Consider the shape of the pupil. In some animals, the pupil changes shape to sharpen their view of the world. In species such as goats, cats, and certain amphibians, the pupil forms a shape perfectly tailored to the ecological needs of the animal. Think of the grazing goat. Its horizontal pupils broaden the field of view, creating a panoramic awareness. This allows them to monitor the horizon for approaching danger while they peacefully feed on the grass. Contrast this with the cat. Vertical pupils enhance depth judgment for predators. They rely on accurate strikes during an ambush, and that vertical slit helps them calculate distance with precision. The shape of the opening affects how light enters the eye and how the lens bends that light. This alters the clarity of objects at various distances. These designs also help manage bright sunlight or dim twilight conditions. The pupil is not merely a circular gateway, as it is in us. It is an adjustable aperture, sculpted by environmental pressures. Each form offers advantages matched to the lifestyle of the species, demonstrating the incredible versatility of optical evolution. Whether a slit or a rectangle, each eye is a masterpiece of biological engineering. Now, let us shrink down to the size of an insect. Some creatures have compound eyes with hundreds, sometimes thousands, of working units. Insects such as dragonflies and bees view the world through eyes composed of many small facets known as ommatidia. Each facet collects light from its own tiny portion of the environment, producing a mosaic-like representation of the world. This arrangement allows for exceptional sensitivity to motion, because changes in one tiny facet stand out clearly from its neighbors. Nothing escapes their notice. Some species have regions with especially dense clusters of these ommatidia for tracking prey or navigating through cluttered spaces. Although compound eyes do not produce the same fine single-image detail as the human fovea, they excel at wide-angle vision and rapid response. Each unit has its own lens, its own photoreceptors, and its own dedicated neural pathway. It forms a distributed network that captures environmental changes almost instantly. The resulting visual world is fast, expansive, and well-suited to the demands of flight or swift movement. It is a world of pixelated clarity, where every movement is registered in a grand, shimmering mosaic. Let us sink beneath the waves now, into the cool, dark water. Here, the octopus evolved an eye that mirrors ours through a process called convergent evolution. In the dark water of ancient seas, two very different branches of life solved the challenge of image-forming vision in remarkably similar ways. And cephalopods, like the octopus, on another. Both developed organs with corneas, lenses, irises, and retinas arranged in comparable layouts, despite having distant ancestry. Yet, the details of construction differ in telling ways. In octopuses, the photoreceptors face the incoming light directly. This avoids the blind spot that exists in our eyes, where vertebrate nerve fibers must leave the eye. The supporting tissues, the embryonic development, and the molecular building blocks also follow distinct rules. These similarities and differences provide a powerful example of how natural selection can discover similar overall designs when facing similar problems. The octopus uses its visual system for camouflage, navigation, and complex behavior. It relies on an organ that feels eerily familiar to anyone who studies anatomy. Two very different minds, one with a backbone and one without, look out on the world through structures that echo one another across deep, evolutionary time. It is a shared solution to the beautiful problem of seeing. Bring your attention back to yourself for a moment, to your own eyes. Did you know that your eyes constantly make tiny movements to prevent the world from fading away? Even when you try to hold your gaze perfectly still, microscopic motions ripple through your eye muscles. These shifts are not mistakes. They are essential to vision itself. Photoreceptors tire quickly when exposed to an unchanged pattern of light. If an image remained completely fixed on the retina, the receptors would adapt. They would stop firing, and the world would begin to fade into a pale blankness. To prevent this loss, the eyes generate constant jittering movements, known as microsaccades, along with subtle drifts and tremors. Each motion refreshes the pattern of light by shifting it across neighboring cells. The brain then blends these refreshed glimpses into a stable scene, giving the illusion of stillness. Artists sometimes notice this effect when staring at a single point for too long, watching the surrounding colors dim. These tiny adjustments also sharpen edges, help detect fine details, and maintain focus during quiet moments of thought. Without this ceaseless dance of motion, vision would collapse into silence. It reveals just how active sight truly is beneath the surface of awareness. Your eyes are dancing, even when you are still. And what of color? Some animals see colors that humans cannot even imagine. For many creatures, the spectrum that feels complete to a human is only a narrow slice of possibility. Birds, reef fish, and many invertebrates carry additional types of light-sensitive cells tuned to wavelengths that fall beyond human perception. Where a person sees a plain petal or a simple feather, these animals may see intricate maps of contrast, glowing signatures that indicate food, mates, or hidden danger. Their brains are wired to interpret combinations of signals that never occur in a human retina, creating hues and blends that do not have names in any language. Color, in that wider sense, is not only a physical property of light, it is a biological invention of each species. What feels like a full rainbow to a human observer is only one design among many. Imagining how a butterfly or a starling views a garden is like trying to imagine a new primary color. Their world is painted with dimensions of radiance that sit forever outside human experience. Yet, they are all around us, humming silently in the shared daylight. It is a secret art gallery, open only to those with the keys to see it. The human eye is more than a camera. It is a living window into the brain. Behind the colored ring of the iris and the dark pupil lies a direct line into the deepest parts of the nervous system. Light enters, but what truly forms is not a picture on a surface. It is a pattern of signals that races along delicate fibers into regions that shape thought, memory, and emotion. Visual information mingles with past experiences, with expectations and fears, and with quiet hopes carried for years. A single glance can trigger a flood of recollection, a shift in mood, or a sudden insight, all because these pathways reach into the same circuits that govern feeling and identity. When a person studies a painting, reads a face, or gazes at a distant skyline, the eye is feeding the brain with streams of ordered energy, and the brain answers by composing meaning. In that sense, vision is not simply received, it is actively created. The eye lets the outer world touch the inner world. Every scene becomes a bridge between the physical landscape and the private universe of the mind. It is humbling to realize that eyes can detect a single photon under perfect conditions. The smallest unit of light, a lone particle crossing the darkness, is unimaginably faint. Yet, the visual system is tuned with such delicacy that receptors can register its arrival. In carefully controlled experiments, people sitting in complete darkness can sometimes correctly report the presence of a single quantum of light entering the eye. Inside the photoreceptors, molecules are configured so that the touch of that one particle can flip a chemical switch. That change triggers a cascade of amplification, like a whisper passed through a chain of sensitive microphones, until the signal becomes strong enough for the brain to notice. Everyday life is far noisier, filled with scattered photons, internal biological fluctuations, and constant movement. So, this exquisite sensitivity is usually hidden beneath the blur of normal experience. Yet, it is always there, a reminder that vision operates at the edge where physics and biology meet. The same organs that handle bright midday scenes also have the potential to respond to the faintest possible trace of light that nature can offer. You are sensitive to the universe in ways you rarely realize. Deep inside the eye, the retina is actually an extension of the central nervous system. At the back of the eye sits a thin, layered sheet of tissue that is far more than a passive screen. It is formed from the same developing material that creates the brain and spinal cord, and it maintains many of the same types of neurons. In those layers, light-sensitive cells connect to intricate networks of interneurons. These networks compare, sharpen, and shape the signals long before they ever leave the eye. Some of these cells emphasize edges, others highlight motion, and others calculate contrasts between neighboring regions of the image. There are circuits that respond specifically to darkening, to brightening, to small points, or to gentle gradients. By the time information reaches the long fibers that carry it deeper into the skull, much of the raw data has already been distilled into meaningful patterns. This internal processing explains why a change in lighting or focus can transform what is noticed in an instant. The structure inside the globe of the eye is, in a very real sense, brain tissue moved forward toward the light. It works tirelessly to turn photons into organized signals, pre-digesting the world for you. Let us return to the deep ocean. Some deep-sea creatures have mirror-based eyes instead of lens-based eyes. Far below the surface, where sunlight fades into a permanent twilight, evolution has explored unusual designs for gathering the few surviving rays. Certain crustaceans and fish have developed eyes lined with layers of reflective crystals that function like finely tuned mirrors. Instead of bending light through a transparent lens, these structures bounce and concentrate it onto the light-sensitive surface, a little like a precision satellite dish focusing faint radio waves. The arrangement of the mirror segments can be adjusted as the animal grows, allowing the organ to stay efficient as body size changes. In some species, the reflective elements are arranged to reduce blur from different wavelengths, solving optical problems in a way quite different from glass lenses. The result is vision adapted specifically for dim and blue-shifted light that filters down from above. In the quiet darkness of the deep ocean, these mirrored organs collect and redirect what little illumination exists. They grant their owners the ability to see silhouettes, glows, and subtle movements that would otherwise vanish into black water. Welcome back to the water. Let us drift a little shallower now, to the sun-dappled reefs where the light plays across the sand. Here, we find a creature with a visual system so advanced, it seems almost alien in its sophistication. The mantis shrimp has the most complex eyes known on Earth. Imagine seeing the world not just in the three primary colors that we do: red, green, and blue, but through 12 or even 16 different color channels. This small marine hunter carries visual organs that are mounted on stalks, moving independently, scanning the water like a built-in sensor array. Within the central band of its eye, there lie numerous types of photoreceptor cells. Some respond to deep, invisible ultraviolets. Others detect different states of polarization, the very direction that light waves are vibrating. This gives these animals access to patterns in light that are entirely hidden to most creatures. They see a secret code written in the water itself. Each eye can judge depth on its own, a feat we cannot match with a single eye. This is because different rows of receptors view the world from slightly offset positions within the same organ. Even one eye can perform complex distance calculations. While we can never truly know what it feels like to be a mantis shrimp, the physical machinery suggests a visual world filled with cues and subtleties beyond our ordinary imagination. It is a world of vivid, exploding color and geometric precision, hidden right here, beneath the surface of our shared ocean. Now, let us return to the human experience. To your experience, think about the edges of your vision. Human peripheral vision is wired for motion, rather than detail. Away from the center of your gaze, the retina shifts its priorities. The outer regions contain more light-sensitive rod cells and fewer fine detail cone cells. This creates a zone that excels at catching movement and changes in brightness, rather than reading text or seeing color. Neural circuits in these areas favor broad shapes. They notice sudden shifts. They detect looming objects over fine patterns. When something moves at the edge of your awareness, a leaf falling, a shadow shifting, the signal reaches your attention quickly. Even if the form remains blurry, this arrangement reflects deep, ancient evolutionary pressures. For our ancestors, the early detection of a predator or an approaching object was far more valuable than the ability to read the texture on a leaf at the margin of sight. Even today, a flicker in your peripheral view can interrupt your concentration on a screen or a page. It happens because those older warning pathways still carry weight. They are silent guardians, watching the boundaries of your world so that you can focus on the center. And what of the eyes themselves? It is a beautiful thought that no two eyes in the world create the same pattern of light and shadow. Every pair of eyes is shaped by a unique history. Genetics, development in the womb, and a lifetime of experience all result in subtle differences in curvature, clarity, pigment, and internal structure. The cornea bends light according to its exact, singular contour. The lens has its own unique arrangement of transparent fibers. The distribution of photoreceptors varies across the retina, like a unique scattering of stars in the night sky. Even tiny variations in pupil size or iris texture change how light enters and spreads. And on top of that, each brain learns to interpret visual input based on personal history, habits, and cultural context. Two people looking at the same scene, a sunset, a painting, a face receives slightly different mosaics of brightness and color. They then apply distinct internal filters, shaped by memory and attention. For one observer, a landscape might highlight paths and human structures. For another, it may emphasize the shapes of trees or patterns of shadow. This individuality means that every moment of sight is a singular event. It is a blend of physical optics and neural interpretation that belongs only to one living observer at that one point in time. Your view of the universe is yours alone. Let us journey deeper, to the very back of the eye. Here lies the fovea, a structure that gives you high-resolution vision in a space smaller than a grain of sand. Near the center of the retina, there is a tiny circular pit packed with cone cells arranged for extraordinary precision. This minuscule zone is the only reason you can read the letters on this screen, thread a needle, or recognize the subtle lines of a loved one's face at a glance. Although the fovea occupies only a tiny fraction of the entire visual field, the brain devotes immense processing power to the signals that flow from it. Every time your eyes dart to something interesting, you are positioning this tiny grain of sand directly over the object so that its details can be examined with maximum clarity. Outside this region, vision becomes softer, dreamier, dependent on motion and contrast. But here, in the fovea, the world is sharp. The structure works so well because each cone connects to its own dedicated neural pathway, preserving the sharpness of the original signal. It is a tiny architectural masterpiece, a biological camera lens of the highest order, allowing you to appreciate the intricate beauty of the world. From this tiny point of focus comes an explosion of color. The human eye can differentiate millions of shades of color. Within the retina, three major classes of cone cells respond to overlapping ranges of wavelengths. But the magic happens in the comparison. The brain compares the relative activity of these cones to generate a vast, seamless range of hues. Subtle shifts in stimulation create delicate gradations that fill the world with nuance. The difference between the green of a new leaf and the green of moss, the shift from the blue of the sky at noon to the indigo of twilight. Over a lifetime, the visual system continually refines this sensitivity. It learns through experience. With practice, a person can become even more adept at noticing fine distinctions between related shades. Artists, gardeners, and scientists often train this ability simply by looking. Under natural lighting, the visual system can detect slight differences that reveal ripe fruit, healthy vegetation, or atmospheric changes before they become obvious. Even though the underlying hardware consists of only 3 types of sensors, the interaction between them produces an immense, limitless palette. The richness of your world depends on this quiet, computational orchestra playing in your mind. How do we know where things are? The ability to see depth comes from a harmony of micro-timed signals. Your perception of 3-dimensional space relies on more than simply having 2 eyes. It is a symphony of data. Each eye receives slightly different information about distance, angle, and motion. The brain merges these signals with astonishing speed. It uses tiny differences in timing and position to construct a sense of depth. Even the movement of your own head provides additional clues, as nearby objects shift more noticeably than distant ones, a phenomenon called parallax. Muscles in the eyes report their level of strain when focusing and turning inward, offering still more information to the brain. All these cues must arrive in well-orchestrated sequences. If the timing is disrupted, depth becomes uncertain and the world can appear flat. But when everything aligns correctly, which it almost always does, you navigate crowded rooms, you catch moving objects, and you judge distances with remarkable ease. The smooth coordination that produces depth perception is one of the brain's most elegant, invisible achievements. It builds the stage upon which your life plays out. It may feel continuous, but your brain reconstructs reality from rapid flickers of visual data. Light reaches the eyes in a continuous stream. Yet, the brain processes vision as a sequence of discrete updates. Neurons fire in rapid bursts, each carrying partial information about color, brightness, movement, and form. The brain must weave these fragments into a seamless world. It is a master storyteller. It predicts what should come next. It fills in the gaps. It smooths the transitions so that motion appears fluid rather than jittery. This reconstruction process happens unconsciously and incredibly fast. When something unexpected occurs, the brain adjusts its predictions and recalculates the scene in an instant. Much of what you perceive in any moment is, therefore, a blend of incoming signals and internal expectations. This dynamic process keeps you oriented in a changing environment. It enables you to read facial expressions, track moving objects, and maintain balance. The stable reality you experience right now is a masterpiece of constant, gentle interpretation. Let us focus on the surface of the eye for a moment. The cornea is one of the most densely innervated tissues in the body. The transparent front surface of the eye contains an intricate web of nerve endings that extend into its layers. These nerves protect the eye by responding quickly, instantly, to irritation, dryness, or foreign particles. Even a slight disturbance triggers a blink or the production of a tear, preserving clarity and preventing injury. This sensitivity exists because the cornea lacks blood vessels. It relies on a delicate balance of moisture and oxygen from the air and tears. Any disruption threatens its transparency, and therefore the quality of your vision. The dense innervation also helps regulate healing processes. Despite its vulnerability, the cornea maintains remarkable resilience. Its structure allows light to pass with minimal distortion, while its nerves ensure that even small hazards are detected swiftly. This combination of transparency and vigilance keeps the window of the eye clear. It is a shield made of sensitivity. There is a secret in every eye. A tiny blind spot in every retina disappears through brain interpretation. Where the optic nerve exits the eye to travel to the brain, there are no photoreceptors. This creates a small region incapable of detecting light a hole in your vision. Yet, you never notice a black spot in your view. Why? Because the brain fills it effortlessly. It draws from the surrounding colors, textures, and patterns to create a seamless image that appears uninterrupted. This process is not random guessing. It is a highly trained synthesis shaped through years of experience. When an object crosses this region, the brain predicts its continuation based on motion and context, preserving the illusion of completeness. Experiments that reveal this blind zone often surprise people because the effect is always active, hiding a structural gap that would otherwise interrupt your perception. The filling-in mechanism highlights how much of sight relies on interpretation rather than raw input. Instead of simply receiving images, your brain constructs them. It smooths imperfections. It merges signals. It ensures continuity. This compensation works so well that only deliberate tests expose the invisible patch each of us carries. And finally, let us look up. The human eye can resolve the glow of distant galaxies with patience and darkness. Under a clear night sky, far from the bright lights of the city, the naked eye can detect faint smudges of light. One of these is the Andromeda Galaxy, an island of stars far beyond our own Milky Way. These distant glows represent clusters of stars so numerous that their combined radiance reaches Earth despite unimaginable distances. The ability to perceive these faint signals depends on chemical processes in the rod cells of your eyes. As you stand in the dark, these cells become more sensitive over time. They adjust, shedding the memory of the bright day, increasing their capacity to detect small amounts of incoming light. With steady attention, the brain enhances subtle contrasts. It recognizes diffuse shapes that would otherwise remain invisible. Although the details remain soft, the recognition of those remote islands of stars connects the human observer to cosmic structures that lie across vast stretches of space. When you gaze at these dim patches, you are witnessing ancient light. It has traveled through near emptiness for extraordinary spans of time, millions of years, before meeting the delicate tissues of your eye. You are touching the history of the universe with your gaze. Let us step into the shadows of a mossy forest. The sun has set, and the world is painted in shades of deep indigo and black. Here, some frogs can see in nearly total darkness. In these shadowed forests and murky wetlands, certain frog species rely on eyes adapted for extreme low-light conditions. Their retinas contain unusually large rod cells, far larger than ours. These cells are capable of capturing scattered photons that bounce through dense vegetation or across the dark, reflective surface of a pond. These cells operate with remarkable sensitivity. They allow the frog to detect the slide of a beetle or the sway of a leaf, even when the environment appears pitch black to a human observer. The shape of their pupils also shifts dramatically, broadening to admit the maximum possible light. Some species even possess reflective layers behind the retina that redirect unused photons back through the photoreceptors, giving the visual system a second chance to absorb them. Their world at night is not a featureless void. It is a landscape patterned with faint silhouettes and subtle motions. It is a world of quiet clarity, guiding them through the thick undergrowth with confidence. Bring your awareness back to your own body, to your eyelids. Your eyelid blinks in rhythms that change with your emotions. Blinking seems automatic, a simple mechanical action to clean the eye. Yet, its timing subtly reflects your inner states. During calm concentration, blinks may occur less often, preserving a steady, uninterrupted flow of visual information. But during moments of uncertainty, or when you are thinking deeply, blink frequency often increases. It is as if the mind is shifting attention between the external scene and internal reflections. Emotional states influence this rhythm as well. Surprise can halt blinking temporarily, a frozen moment of processing. Worry or fatigue may accelerate it. The eyelid is controlled by a delicate interplay of voluntary and involuntary muscles, guided by neural circuits sensitive to your mood. Beyond moisture regulation and protection, blinking contributes to mental pacing. It punctuates thought. It offers tiny pauses, microscopic rests that help the brain transition between ideas. These tiny closures are a continuous, silent conversation between your body and your mind. Now, imagine the silent flight of an owl. Owls have eyes so large they cannot move in their sockets. Unlike our eyes, which are spherical and rotate freely, an owl's eyes are large and tubular. They are shaped like telephoto lenses, packed with photoreceptors optimized for dim environments. This shape provides incredible magnification and light-gathering power, but it comes at a cost. There is little room for rotation inside the skull. This means the bird cannot glance sideways. It cannot dart its eyes to the left or right. To compensate, owls evolved remarkable flexibility in their neck vertebrae. They can rotate their heads through impressive arcs that far exceed human capability up to 270 degrees. This ability lets them maintain a wide field of surveillance while perched silently in the darkness. The combination of large, stationary eyes and agile neck movement creates a highly effective system for night hunting. With their heightened sensitivity to faint motion and their capacity to reposition their gaze instantly by turning their head, owls can detect and target prey with uncanny accuracy. It is a design of perfect stillness, followed by precise movement. Let us look closely at the color blue. If you have blue eyes, or know someone who does, you are looking at a trick of the light. The blue color of eyes comes from scattered light, not pigment. Unlike brown or hazel eyes, which contain melanin, blue irises contain very little pigment. The hue arises from the way light interacts with the microscopic structure of the iris stroma. It is the same physics that makes the sky blue. It is called the Tyndall effect. The collagen fibers in the iris scatter shorter blue wavelengths of light more efficiently than longer red wavelengths. This scattered light reflects back to the observer, creating the appearance of blue. Variations in the fiber density and arrangement lead to a wide range of shades, from pale, icy tones to deep ocean azure. But there is no blue ink in the eye. This structural color means the eyes can shift slightly with the angle of light or the brightness of the room. It is a color created by physics, a reflection of the atmosphere held within a gaze. Travel now to the calm waters of a mangrove swamp. Here, a unique fish swims right at the surface line. Some fish can look up and down at the same time. Species like the anabelps, often called the four-eyed fish, inhabit the interface between water layers. They need to know what is happening in the air above them. Perhaps a bird is swooping down, and what is happening in the water below. Perhaps a larger fish is rising. To achieve this, they possess eyes divided into functional regions. The upper half of the eye is adapted for viewing the brighter, airy world above. The lower half functions in the dimmer, refractive underwater surroundings. Each region has a lens curvature tailored to its specific lighting environment. This arrangement allows the fish to detect predators from the sky while also monitoring prey below. The division is not a simple split, but an elegant optical compromise shaped through generations of selection. By maintaining watch in two worlds at once, they stay alert to changing conditions. They are the guardians of the horizon line. Turn your thoughts inward again, to the heavy, quiet work of your own brain. Human vision uses more of the brain than any other sense. Large regions of the cerebral cortex are devoted almost entirely to interpreting visual information. It is a massive undertaking. Signals from the eyes pass through multiple processing stages. Another maps where things are in space. As these layers merge, they form coherent scenes filled with meaning. Additional areas integrate vision with memory, language, and decision-making. This extensive network reflects the complexity of transforming raw light into perception. The brain must constantly filter, group, and prioritize incoming stimuli. It selects what to focus on while ignoring distractions. Vision also interacts with systems controlling movement, allowing you to adjust your posture or coordinate your hands. The sheer scale of neural involvement shows how central sight is to the human experience. Every moment of seeing represents an immense collaboration among countless cells working in perfect, silent synchrony. In the insect world, the sky provides a map that we cannot see. Some insects can perceive the polarization of sunlight. Dragonflies, ants, and bees detect the orientation of light waves as they scatter through the atmosphere. This ability allows them to determine direction even when the sun is hidden behind clouds. Specialized photoreceptors in their eyes respond differently depending on how the light is polarized. By comparing signals across the eye, insects create maps of sky patterns that act like natural compasses. These patterns change with the position of the sun, offering reliable cues for navigation throughout the day. In open landscapes, polarization vision helps insects travel long distances, locate water, and return to their nests with precision. For creatures equipped with this sense, the sky is not just a dome of blue or gray. It is a grid of geometric information, a series of lines and arcs that guide purposeful movement across the earth. We often think the brain does all the thinking, but the eye has its own intelligence. The retina contains layers of neurons that pre-process images before the brain even sees them. As light enters the eye, it passes through a series of interconnected cells that begin refining the raw signal immediately. Some neurons emphasize edges by comparing brightness between neighboring areas. Others detect the direction and speed of movement. Still, others adjust sensitivity in response to changing light levels. This pre-processing reduces the burden on higher brain centers by organizing information into manageable streams. It acts like a biological circuit board. By the time signals reach the optic nerve, the image has already been filtered, sharpened, and prepared for interpretation. This early refinement allows for fast reactions and accurate perception in environments filled with complexity. The eye is not just a camera, it is a computer. Think back to the very beginning, to the time before you were born. The human eye begins forming within weeks of early development. Before a heartbeat becomes steady, before limbs take shape, a pair of small, outward folds begins to form on the early nervous system. These folds deepen, widen, and eventually create the foundations of the eyes. Even at this delicate stage, chemical gradients and electrical cues determine where future photoreceptors will reside, how the lens will curve, and where neural pathways will extend. As development continues, tiny vessels nourish the growing tissues until the eye reaches a level of structural complexity unmatched by nearly any other organ. The retina forms from the same embryonic layer that shapes the brain, which is why it behaves much like a living extension of neural tissue. By the time a newborn first opens its eyes, millions of intricate connections have already formed. These early visual foundations allow the infant brain to begin mapping the world long before conscious memory appears. Sight is a masterpiece of biological choreography. And finally, let us end with a familiar friend in the darkness. Cats have reflective tissue that amplifies dim light. Inside every feline eye lies a shimmering layer known as the tapetum lucidum. This layer is famous for its ability to magnify faint glimmers of light that pass through the retina. When light enters a cat's eye, some of it slips past the photoreceptors. But instead of being lost, it reaches this reflective sheet. It bounces back through the retina a second time, giving the visual system a double exposure. This significantly increases the sensitivity needed for twilight hunting. As a result, cats can navigate environments where most creatures would see nothing but darkness. The reflective tissue also creates the familiar glow eyes, shining in the night when light catches them. The structure is often arranged to enhance blue and green wavelengths, giving cats an advantage as they stalk across moonlit landscapes. Their night vision feels almost supernatural to us, but for them, it is simply the way the world looks. Come closer now, closer than you usually stand to a mirror. Look into the colored ring of the eye. The iris holds unique patterns that are more individual than fingerprints. Within that circle of color that surrounds the pupil lies a tapestry. It is a woven landscape of delicate fibers, folds, and tiny valleys called crypts. These patterns are so intricate that they rarely resemble another set in the entire world. These variations arise through subtle developmental processes in the womb. They are influenced by genetics, yes, but also by random pressure gradients, the distribution of pigment, and the early movement of tissue. Even identical twins, who share nearly identical DNA, possess irises that differ in their fine structural details. It is a personal signature. Unlike fingerprints, which can wear down with manual labor or change through injury, iris patterns remain remarkably stable over a lifetime. Each ring of color reflects a unique interplay between pigment cells and the underlying muscular structures that control pupil size. Researchers who study the geometry of the eye often marvel at this complexity. What appears to be a simple splash of blue, green, hazel, or brown is actually a biological signature created through countless microscopic events. You carry a unique piece of art in your face, a painting that will never be replicated. Now, let us change our perspective entirely. Let us see the world through the sensation of warmth. Some snakes see heat as a separate visual channel. In certain species, like pit vipers, there are specialized organs near the mouth. These are sensitive membranes that respond to tiny temperature differences in the environment. These structures detect infrared radiation heat with a sensitivity great enough to perceive the warmth of a small animal even in complete darkness. But they do not simply feel warmth like you feel sunlight on your skin. They see it. When combined with normal vision, This thermal channel allows snakes to create a layered perception of their surroundings. They form spatial maps. They see the glowing outline of life against the cool background of the Earth. Neurons within these heat-sensing organs connect to brain regions that help coordinate strikes and navigate the night. This ability gives them an immense advantage. Even a still object, if it is warm, reveals itself through the faint radiation it emits. For these creatures, darkness is not dark. It is a landscape painted in temperature gradients, a world of glowing signals and living heat signatures. Return to the feeling of your own body moving. Think of catching a set of keys thrown to you. Your eyes constantly predict motion before it happens. The visual system never waits passively for information to arrive. It is always guessing. It anticipates changes, projects, trajectories, and prepares the body to respond even before an object completes its movement. When something travels across your field of view, neurons responsible for motion detection fire in patterns that correspond not only to what is happening now, but to what will likely happen in the next fraction of a second. This predictive ability is what smooths motion. It allows fast-moving objects to appear continuous rather than fragmented. It supports everyday tasks, reaching for a cup, catching an object, or simply watching someone gesture. Without prediction, the world would appear delayed. It would feel disjointed because neural signals take time to travel from the eye to the brain. By forecasting motion, the brain compensates for these delays. This mechanism operates constantly, even now. Through prediction, the eyes and brain transform a world in constant motion into one that feels stable, coherent, and calm. Deep inside your eye, there is a part of you that never stops growing. The lens continues to grow slowly throughout a lifetime. Unlike many bodily structures that reach a fixed size in adulthood like your bones, the lens adds new layers of transparent fibers year after year. These layers form concentrically, very similar to the rings inside a tree trunk. This growth gradually increases the thickness of the lens and alters how it bends light. Because the lens lacks blood vessels to bring in new cells, it relies on carefully balanced fluids and internal proteins to maintain its crystal clarity. Over time, this increasing density makes the lens a little stiffer. This is why focusing on close objects becomes more challenging as we age. It is not a failure, it is a result of accumulation. Despite this ongoing growth, the lens remains remarkably flexible for decades, shaping itself quickly to shift focus between near and distant scenes. Its continuing growth is a testament to biological persistence. It is a slow and constant remodeling that supports your vision through every chapter of your life. Imagine having eyes that are not locked together. Some animals can move their eyes independently, like tiny periscopes. Chameleons and several species of fish and reptiles possess eyes capable of swiveling in different directions at the same time. This independence grants them panoramic awareness without requiring a single movement of the head. Each eye gathers separate information. The brain processes these two different streams in parallel. One eye might be monitoring a predator approaching from above, while the other scans the leaves below for prey. When a chameleon finally focuses on a particular target, both eyes eventually align to provide depth perception for the strike. But until that moment, they scan their surroundings with extraordinary freedom. The muscles that control these movements operate with precision, adjusting angles and focus independently. This system allows the animal to conserve energy by keeping its body perfectly still while maintaining high vigilance. It is an elegant blend of surveillance, and stealth, perfectly suited to habitats where motion attracts attention and stillness guarantees safety. Now, stand up and walk across the room in your mind. Notice how the world stays steady. The brain creates a stable visual world despite constant head movements. Every time you walk, breathe, or shift your posture, your head moves in subtle ways. If you were a video camera, these motions would make the footage shaky and unwatchable. Yet, your vision remains steady. This is because the brain uses input from balance organs in the inner ear, the vestibular system, to compensate. When the head tilts or turns, reflexes adjust eye position to counteract the motion. If your head turns left, your eyes reflexively turn right to keep the image stable. This happens instantly. At the same time, higher processing centers interpret shifting signals. They predict which changes arise from your body movement and which arise from real changes in the environment. This combination of reflexive and cognitive compensation allows you to read a sign while walking or look at a face while nodding. The stability of perception depends on the seamless integration of sight and balance. It anchors you in a moving world. Your senses are not isolated islands. They talk to each other. Your eyes and ears coordinate to judge distance with precision. Depth perception involves far more than visual cues. Tiny delays in sound, slight differences in pitch, and the echoes from surrounding surfaces provide crucial information that the brain merges with visual data. When these channels work together, you gain a refined sense of where objects are located in space. This collaboration becomes especially important in environments where visibility changes rapidly, like a crowded room or a dimly lit forest. Muscles around the eyes report the effort required to focus. Meanwhile, auditory circuits calculate how sound travels through the environment. Together, they help determine whether a sound originates from something close or far, moving or stationary. This multi-sensory partnership allows you to navigate with confidence. It is a reminder that your perception is a unified experience, woven from every sense you possess. Let us return to the surface again, to the moisture that makes sight possible. The tear film nourishes and protects the eye in layers of incredible complexity. Covering the surface of the eye is a thin, delicate film, but it is not just water. It is composed of 3 distinct layers, each serving a vital function. The outermost layer contains oils. These oils slow down evaporation and create a perfectly smooth optical surface for light to enter. Beneath it lies the watery layer, filled with nutrients, oxygen, and protective molecules that feed the cornea. And the innermost layer is mucus, which anchors the film to the eye, ensuring it spreads evenly with every blink. This structure is renewed constantly. It is replenished by glands that respond to changes in humidity, irritation, and even your emotional state. The tear film cleans away debris. It maintains clarity. Without it, the cornea would dry and vision would blur. Though nearly invisible, this multi-layered shield demonstrates how even the thinnest features of the eye play essential roles. It is a liquid armor, refreshing itself every time you close your eyes. To a fly, you are moving in slow motion. Some insects see a world refreshed many times faster than humans do. For creatures that zip through the air or dart across open fields, survival depends on noticing changes far more rapidly than a human ever could. Many insects experience visual updates at speeds that feel almost impossible to imagine. Their photoreceptors reset quickly. Their neural circuits transmit signals with incredible haste, and their brains process motion in slices of time so fine that what appears smooth to a human becomes a rapid sequence of distinct moments to them. A dragonfly weaving through a swarm perceives trajectories with clarity. It can adjust its flight path in an instant. A fly escaping a swatting hand reacts not because it is lucky, but because the world, to it, unfolds in many more perceptual frames. This accelerated refresh rate means that danger and opportunity emerge earlier in their awareness. It grants them a level of agility that astonishes researchers. Their high-speed perception does not merely sharpen their vision. It shapes an entirely different experience of reality. They live in a faster time. Sometimes, your brain invents movement. Human vision can be tricked into seeing motion that is not there. The brain builds motion from changing patterns of light rather than from motion itself. This means it can be persuaded to detect movement where none exists. When certain shapes alternate, or when high-contrast patterns are arranged in specific ways, the visual system interprets the sequence as shifting, sliding, or rotating. This occurs because the brain expects continuous flow. It fills transitions with imagined progression. Even static images can inspire a sense of drift. These illusions reveal the shortcuts used to create smooth perception. Instead of analyzing every tiny change in detail, the brain relies on predictions and pattern completion. When those expectations are nudged in specific ways, the result is a compelling but entirely fictional sense of motion. Such illusions highlight how perception is an active process. It is shaped by assumptions, biological limits, and the brain's desire for a coherent story. Imagine standing in the middle of a deep, ancient forest. Look around you. The color green is perceived with extraordinary sensitivity through evolution. Across countless generations, our early ancestors lived their lives among the trees. They relied on the ability to distinguish subtle variations in vegetation. Was that fruit ripe? Was that branch sturdy? Was there a predator hiding in the dappled shade? This necessity shaped the development of exceptionally fine tuning within the visual system for the wavelengths associated with green. Our cone cells respond strongly to this region of the spectrum, and neural circuits amplify these signals with remarkable precision. As a result, slight differences in foliage appear distinct to us. We can see the difference between the pale green of a new shoot and the dark, waxy green of an old leaf. This heightened sensitivity remains deeply woven into modern perception. It is why people often report that the color green feels restful. It feels like home. When you look at a garden or a forest, your eye and brain are handling the information with unusual efficiency. It is a biological preference, a perceptual legacy from the forest floor that still whispers to us today, telling us that here, surrounded by green, we are safe. Now, lift your wings and soar, higher and higher, until the world below looks like a map. Certain birds of prey can see small animals from heights that seem impossible. High above open fields, eagles and hawks circle. They possess eyes capable of resolving details far beyond human ability. Their retinas hold exceptionally dense clusters of photoreceptors, sometimes 5 times more dense than our own. Some species even possess more than one foveal region. They have one for looking straight ahead and another for looking sideways with pinpoint accuracy. Light entering these eyes is processed with exquisite precision. A tiny rodent scurrying beneath leaves becomes visible even from dizzying altitudes. The bird's visual machinery extracts detail from minute contrasts and faint motions that we would never see. The shape of their eyes, the strength of their focusing muscles, and the unique architecture of their retinas work together. They create clarity unimaginable for most species. What appears to a human as a blur or a patch of brown landscape appears to them as a rich tapestry. It is filled with meaningful signs. They read the earth from the sky. Turn your attention inward again, to the hidden protection within you. The eye has built an immune privilege to protect its delicate structures. Inside the eye, tissues perform vital functions that would be threatened by the swelling and heat of normal inflammation. To preserve clarity and prevent damage, the body maintains special immunological rules within this sensitive environment. Immune cells behave differently here. They are quieter. They respond in controlled ways that reduce the risk of scarring or clouding. Chemical signals, moderate inflammation, and physical barriers limit the movement of certain cells that might disrupt the transparent architecture. This protective strategy is known as immune privilege. It is a sanctuary within the body. Although this system enhances safety, it requires careful balance. Infections must still be managed, but without the chaos of a full immune response. The existence of immune privilege underscores the profound importance of vision. The body knows that maintaining a clear window to the world is worth creating a special set of rules. We spoke of blinking before, but consider the magic of what you don't see. Your brain fills in missing details every time you blink. Each blink interrupts the flow of incoming light. For a fraction of a second, you are in darkness. Yet, you never perceive the world stutter. You never see the lights go out. Instead, the brain stitches the moments together. It smooths over the interruptions so thoroughly that you remain unaware of them. This requires rapid prediction and reconstruction. Before your eyelids close, the brain gathers information about ongoing motion, color, and spatial layout. During the blink in that tiny moment of darkness, it generates a provisional continuation of the scene. It uses context, expectation, and memory to guess what is happening. When the eyes open again, the updated input merges seamlessly with this internal projection. The result is a sense of continuous vision. This process highlights the extraordinary computational effort required to maintain stable perception. Every blink becomes a fleeting pause that the brain conceals through elegant, efficient interpretation. It is editing the movie of your life in real time. Look into the eyes of someone you love. The pupil responds to thoughts and emotions as well as light. Although its primary function is to regulate incoming brightness, the pupil is also a window into the mind. When a person becomes interested, surprised, or emotionally moved, small muscles within the iris respond. The opening may widen when attention intensifies. It expands when cognitive effort increases, like when you are solving a difficult puzzle. In social situations, pupils can shift in ways that subtly communicate engagement, trust, or attraction. These changes are not consciously controlled. You cannot will your pupils to dilate. They arise from deep connections between the visual system and the autonomic nervous system. Even imagined images or remembered scenes can trigger measurable responses. If you close your eyes and imagine a dark room, your pupils might change. This interplay reveals that the eyes do more than gather light. They mirror the shifting patterns of thought and feeling that flow through the mind. They speak a silent language of connection. Let us return to the gentle grazers of the field. Some animals have rectangular pupils to enhance horizon awareness. Grazing animals such as sheep, goats, and horses possess pupils shaped in long, horizontal bands. These are not round like ours, nor vertical like a cat's. This geometry expands their field of view across wide landscapes. It allows them to monitor potential threats approaching from many directions behind, to the side, in front, while keeping focus on the food close to the ground. But here is the most fascinating part. When these animals lower their heads to feed, their eyes rotate in their sockets. This rotation keeps the rectangular pupil aligned with the horizon. This automatic adjustment keeps their panoramic vision functional even while they are eating. It offers a broad visual sweep that helps prey detect danger before it draws near. It is a design for peace, allowing them to graze safely under the open sky. Your eyes are also your clock. The retina contains cells that track daylight to regulate sleep. Among the many cells embedded within the retina are specialized, light-sensitive units that do not help you see pictures. They are not for vision. Instead, they monitor overall brightness. These cells respond strongly to the blue-rich light of the morning sky. They send signals directly to the brain areas that coordinate circadian rhythms, your internal body clock. When morning light strikes them, they tell the brain to wake up, to release cortisol, to warm the body. When daylight fades, their reduced activity informs the brain that night is approaching. This triggers the release of melatonin, preparing the body for rest. The presence of these non-visual photoreceptors demonstrates that the eye participates in regulating much more than sight. It anchors the rhythms that shape your daily life. It connects your internal time to the rotation of the earth. Step into the dark now. Wait, humans can adapt to low light far more than most people realize. Although our night vision cannot match that of an owl or a cat, the human visual system becomes dramatically more sensitive after extended time in darkness. Rod cells increase their responsiveness through chemical adjustments. They regenerate a pigment called rhodopsin. This allows them to capture faint photons that would otherwise go unnoticed. The brain recalibrates its expectations. It amplifies subtle contrasts. It suppresses the noise that might interfere with dim signals. With patience, usually about 20 to 30 minutes, details that first appeared hidden begin to emerge. A seemingly black environment transforms into a scene filled with outlines and gentle shades of gray. This adaptation takes time. It requires you to slow down. Once achieved, it reveals an impressive capacity within the human eye that often goes unused in our brightly illuminated modern world. It is a hidden superpower, waiting for the lights to go out. Beneath the waves, the dark is not always dark. Some creatures use fluorescent patterns, visible only under specific wavelengths. Across coral reefs and forest floors, live animals whose bodies carry hidden markings. These emerge only when illuminated by very specific wavelengths of light. This is fluorescence. It happens when specialized molecules absorb incoming light and re-release it as a different color, often brighter, more vivid, neon. Many fish display glowing stripes or patches that guide communication in dim or murky water. Certain amphibians exhibit luminous markings that identify species. Even some birds show fluorescent features. These displays allow animals to send messages that remain invisible to predators who lack the necessary sensitivity. It is a private channel, a secret language encoded in the physics of light. When researchers place these animals under the correct illumination, entire dimensions of their appearance spring to life. It shows us that nature often reserves its brightest secrets for those tuned to the right frequency. Finally, think of the delicate balance inside the eye itself. The eye maintains pressure with remarkable biological precision. Inside the eye, a clear fluid known as aqueous humor continuously circulates. It delivers nutrients to tissues that lack blood vessels. But for vision to remain sharp, the pressure created by this fluid must stay within a very narrow range. If it becomes too low, the eye loses its shape, like a deflated balloon. If it becomes too high, delicate neural fibers risk damage. To maintain equilibrium, the body regulates production and drainage with exquisite control. Tiny structures filter the fluid. Microscopic channels adjust the flow in response to your posture, hydration, and even your heartbeat. This system recalibrates moment by moment. The balance is so consistent that most people never notice the complexity required to maintain it. It is a quiet, hydraulic miracle, operating silently to keep the window of your soul clear and strong. Let us sink to the very bottom of the world, into the crushing, silent darkness of the deep sea. Here, some deep ocean fish have eyes larger than their entire heads. In this realm, where sunlight fades into memory, certain species rely heavily on vision despite the near total absence of illumination. To gather every possible photon, every stray particle of light evolution has pushed the boundaries of anatomy. Some fish develop enormous eyes that dwarf the size of their own skulls. These oversized organs contain vast surfaces of photoreceptors designed to capture faint glimmers produced by other bioluminescent creatures drifting through the water. The lenses in these eyes are often exceptionally wide, maximizing light intake. The retinas carry layers of rods arranged to enhance sensitivity rather than detail. Because these fish inhabit depths where distances are difficult to judge, their vision favors detecting contrast and silhouette. The massive size of the eye is an adaptation that would be impractical in brighter environments. But here, it is essential. Observing these animals reveals how extreme environments push nature to explore possibilities that seem almost surreal. They are living telescopes, pointing into the dark, waiting for a spark. Travel back in time with me now, millions of years. Human color vision originated from a single gene duplication in ancient primates. Long ago, early primates possessed only two types of cone cells. Their world was painted in yellows, blues, and grays. They could not distinguish red from green. Then, a rare event occurred. A gene responsible for one type of photopigment duplicated itself. It was a genetic accident. Over time, mutations caused this copy to become sensitive to a slightly different range of wavelengths. This small change set the foundation for the rich color perception that you experience right now. Having three cone types allowed individuals to differentiate ripe red fruits from green leaves. It allowed them to spot fresh vegetation. This advantage influenced foraging behavior, social interaction, and habitat selection. As the system evolved, neural circuits adapted to handle increasingly complex comparisons among wavelengths. The result is the sensory palette capable of generating millions of distinct shades. The origin of your ability to enjoy a sunset lies not in a grand plan, but in a happy accident that transformed the way we see the world. Your brain is not a machine made of hard metal. It is a garden. The visual cortex can rewire itself after injury with incredible plasticity. When areas of the brain that interpret sight become damaged, or when vision changes, the surrounding regions often reorganize themselves to compensate. Neurons adjust their connections. They strengthen alternative pathways. Sometimes, they even assume functions once handled by the affected tissue. This plasticity is most pronounced during childhood, but it remains present throughout life. Individuals who lose vision early often show heightened sensitivity in hearing or touch, because visual regions are repurposed to process other sensory inputs. Even in adults, therapy and training can help the visual cortex adapt. Researchers studying this phenomenon observe how neural architecture is not fixed, but dynamic. It is shaped by experience and demand. The ability to reorganize underscores how perception depends on flexible networks. The brain does not simply receive visual information, it learns it continuously. It rebuilds it when necessary. It is always seeking new routes to understanding. In the water, growing up can mean seeing a whole new world. Some animals switch between lens vision and mirror vision during growth. A handful of aquatic creatures undergo developmental transformations that alter the very structure of their eyes. Juveniles may rely on conventional lenses that refract light, giving them clear underwater vision in the shallows. But as they mature and move into deeper, darker, or differently lit environments, these lenses may be partially replaced by reflective surfaces, mirrors. These mirror-based eyes excel in environments where illumination arrives from unusual angles or where refracting lenses would struggle to gather enough light. By shifting from one optical strategy to another, these animals maintain visual efficiency across their changing habitats. The shift involves not only structural remodeling, but also adjustments in the brain to interpret the different types of images. This transformation highlights how nature tailors vision not only to the species, but to the specific moment in a life. It is the ultimate adaptation, changing your eyes to match your journey. Here is a thought to hold gently in your mind. You are always living just a fraction of a second in the past. Your visual world arrives in the brain delayed by a fraction of a moment. Although perception feels instantaneous, it requires time. Time for light to reach the retina. Time to generate electrical signals. Time to travel through complex pathways into the brain. And time for the brain to process what it has received. This creates a tiny delay. If the brain did not compensate, the world would appear slightly outdated. You would miss the ball. You would trip over the step. Instead, the brain uses predictive mechanisms. It estimates what should be happening at the present moment, blending expectations with the signals it received a moment ago. This predictive strategy smooths motion. It stabilizes the environment. It aligns perception with reality, despite the lag. Most of the time, the system works flawlessly. But it means that the now you experience is a construction. It is a blend of what was and what your brain believes is happening. You are surfing on the crest of time, supported by the incredible speed of your mind. Let us look at the butterfly again. Butterflies can see spectral patterns hidden from human eyes. Many butterfly species perceive ultraviolet light. They respond to patterns that remain invisible to human observers. Wings that appear to us as simple colors orange, white, or yellow contain elaborate ultraviolet maps. These maps signal species identity. They signal readiness for mating. They define territorial boundaries. When butterflies encounter one another, these hidden patterns guide their behavior, helping them choose partners or avoid rivals. Flowers, too, display ultraviolet markings. They direct butterflies to nectar sources, creating a mutually beneficial communication channel. The visual system of these insects contains specialized photoreceptors capable of distinguishing subtle differences within the ultraviolet range. As a result, their world is filled with contrasts and cues that we cannot experience directly. The interplay between ultraviolet-sensitive vision and the colorful patterns of nature demonstrates a level of coordination that unfolds just beyond our sight. It is a secret conversation happening on the petals of a flower. Deep inside your own eye, there is a rhythm. The human eye has photoreceptors that each follow their own biological rhythms within the retina. Every single photoreceptor engages in daily cycles of renewal and repair. These rhythms align with your overall sleep-wake cycle, but they also maintain internal schedules unique to their function. Throughout the day, photoreceptors adjust their sensitivity. They rebuild molecular components. They regulate chemical balance to handle the continuous flow of light. It is hard work, catching photons. During sleep, they undergo deeper restoration. They clear away the waste products of the day and prepare for the next morning's visual demands. These rhythms ensure that the retina maintains clarity and responsiveness. When these cycles become disrupted by lack of sleep or bright lights at night, visual fatigue can occur. The presence of such timing mechanisms highlights the sophistication of even the smallest units within the eye. Each photoreceptor behaves as a tiny biological workshop, maintaining its function through predictable, comforting cycles of activity and rest. And finally, let us visit a small, eight-legged friend. Some spiders have 8 eyes, each serving a distinct function. Spiders often rely on multiple eyes, arranged in patterns that vary widely among species, but they do not just see 8 copies of the same image. Instead, each eye type contributes specific information. Some eyes detect motion, others judge distance, and still others, like the large central eyes of the jumping spider, provide detailed, high-resolution, forward-facing vision. The combination allows spiders to hunt, navigate webs, and avoid predators with remarkable precision. Imagine the jumping spider. Its secondary eyes monitor movement from behind and above, acting like a security system. Meanwhile, its primary eyes focus on the target in front. The diversity of visual roles reflects the complex lifestyles of these creatures. Their eyes must operate efficiently in dim crevices, bright daylight, and rapidly shifting terrain. Through this distributed visual system, they gain a comprehensive awareness of their surroundings. It is a 360-degree view of the world, stitched together into one seamless experience. Breathe in the cool air of the morning. Look up at the sky. Humans possess cells that naturally detect the presence of blue light. Embedded within your retina is a rare, special class of cells. They are not the rods that see in the dark, and they are not the cones that paint the rainbow. They do not help you see shapes or read words. Instead, they respond almost exclusively to blue-enriched wavelengths, the color of the sky at the start of the day. These cells contain a light-sensitive molecule called melanopsin. When morning light strikes them, they send a silent signal to the brain. It is a signal that bypasses the visual cortex entirely. It goes straight to the centers that regulate alertness and hormone release. Their purpose is to keep your internal world aligned with the external world. Even on cloudy days, these cells remain responsive because scattered blue light can still penetrate the gray. When you step outside in the morning, you are not just seeing the day. You are plugging yourself into the sky. You are letting the atmosphere calibrate your biology. It is a reminder that we are creatures of the sun and the air, tethered to the planet by the very design of our eyes. Now, imagine you are one of those birds, flying north. Some birds can see magnetic fields through quantum processes. In the eyes of certain migratory birds, such as European robins, lies a remarkable protein. It reacts to the Earth's magnetic field in ways that intertwine the strange laws of quantum physics with the wet, warm world of biology. When specific wavelengths of light strike this molecule, it forms paired particles. The behavior of these particles changes. depending on the orientation of the magnetic field. These changes influence signaling within the retina. To the bird, this might create faint visual patterns, perhaps shifting gradients or shadows that overlay the normal image of the world. Imagine seeing the direction of north as a faint ribbon of light in the sky. To them, direction is not a guess. It is a visible feature of the landscape. This blending of quantum sensitivity and living tissue reveals one of nature's most extraordinary sensory adaptations. They navigate continents using a built-in compass that operates at the subatomic level. Turn your thoughts to the connection between your eye and your mind. The optic nerve carries more information than many digital cameras. Running from the back of each eye is a thick bundle of neural fibers. This is the optic nerve. It transmits an immense stream of signals every single second. But it does not just send raw pixels like a camera. It carries refined information. It tells the brain about brightness transitions, the direction of motion, and localized contrast. The total volume of information flowing through this pathway is staggering. Millions of signals travel simultaneously, forming a river of data that the brain must decode rapidly enough to keep up with the changing world. The optic nerve accomplishes this while maintaining precise timing. Signals must arrive in the correct sequence for interpretation. As a living biological cable, it handles a level of complexity that modern technology continues to struggle to match. It is the highway of your consciousness. Your eyes are never truly resting, even when you are. Your eyes continually balance light intake with microscopic muscle movements. Behind every effortless glance is the coordinated action of tiny muscles. They regulate how much light enters the eye and how sharply images come into focus. The iris tightens or relaxes to control pupil size, narrowing in bright environments and widening when illumination fades. At the same time, muscles encircling the lens adjust its curvature to maintain clarity across different distances. These adjustments must occur with precision, measured in fractions of a millimeter. Even slight delays could blur the world. Additional micro-adjustments stabilize the eyes against small head movements, keeping the visual scene sharp as you breathe. All of these actions blend into a seamless experience that feels effortless. The steadiness of the world you see depends on these near-constant calibrations. They operate quietly, completing thousands of corrections every minute, asking for no praise, simply maintaining the clarity of your life. Let us travel to the dry, shifting sands of the desert. Some desert animals have built-in sand filters within their eyes. Life in shifting dunes requires eyes that can withstand abrasive particles carried by hot, relentless winds. Certain desert-dwelling species have evolved protective structures that function like natural filtration systems. Camels rely on a combination of long, luxurious lashes, specialized lids, and internal folds that trap particles before they reach the sensitive cornea. These mechanisms not only shield the eye but also maintain moisture in extremely dry conditions. The design often includes tear ducts that flush irritants away with remarkable efficiency. In environments where storms can erupt without warning, these adaptations prevent damage. The animals move confidently across landscapes that would quickly injure unprotected eyes. Their visual systems embody the ingenuity of evolution, shaped by the wind and the sand. Back in the water, the rules of focus change. Some aquatic animals can change the shape of their lenses instantly. Creatures living in water often encounter rapid transitions between murky depths, bright shallows, and reflective surfaces. To maintain clarity, some species adjust the curvature of their lenses far more dynamically than we can. In the human eye, the lens changes shape by being pulled by muscles. But in some fish, the lens actually moves back and forth, like the lens of a camera. This rapid adjustment allows them to track prey, navigate cluttered environments, and compensate for the distortions caused by water. Their lens fibers are arranged to retain transparency while allowing flexible movement. Neural circuits coordinate these changes to ensure that the right focal length is achieved at the exact moment it is needed. It is a visual system finely tuned to the fluid, ever-changing nature of the aquatic world. Consider the color of an apple. The eye and brain work together to create the perception of color. Color is not a property that exists fully formed in light itself. Light is just wavelengths. Color emerges when photoreceptors send signals that the brain interprets. The brain examines the ratios of activity between your red, green, and blue cones. But it does something even more clever. It compares the object to its surroundings. This is why an apple looks red whether you are standing in bright sunlight or sitting in a dimly lit room. The wavelengths reflecting off the apple are different in those two situations, but your brain corrects for the lighting. It creates color constancy. Without the brain's contribution, the world would appear as raw variations in intensity. It is the brain that paints the apple red. The creation of color is a partnership between biological hardware and neural poetry. Nature often sees more than our screens can show. Some animals see a wider range of contrast than any human screen can display. Certain species possess retinas capable of handling dramatic differences in brightness. They can look at a scene with deep, dark shadows and blindingly bright sunlight and see detail in both at the same time. Their photoreceptors and neural circuits manage extreme contrasts by adjusting sensitivity locally rather than globally. This allows them to see into the shadows of a forest while still observing the sunlit canopy. In comparison, even the best human television screens simulate only a fraction of this range. These animals experience a world filled with nuance that remains hidden to us. Their sensitivity gives them access to patterns that blend into uniform fields for other species. They see the texture of the light itself. Close your eyes for a moment. Do you see fading shapes? Humans experience afterimages because photoreceptors need time to reset. When you stare at a brightly colored object and then look away, a faint, ghostly shape often appears in complementary colors. If you stare at green, you see magenta. If you stare at blue, you see yellow. This occurs because the photoreceptors that were heavily stimulated get tired. They take time to return to their baseline state. During this recovery period, the balance shifts to the other photoreceptors, producing the illusion of a lingering image. The effect highlights the biochemical processes underlying vision. Each photoreceptor relies on molecules that change shape when exposed to light. They must physically revert to their original form before responding normally again. Afterimages reveal the hidden rhythms of these molecular cycles. They demonstrate that perception does not end the moment you look away. It fades gradually, like a bell that continues to hum after it has been struck. Let us end this part in the deep blue sea again. Some shrimp species generate light to enhance their vision. In the dim world of deeper waters, certain shrimp do not just wait for light, they make it. They produce their own bursts of bioluminescence using chemical reactions. But here is the brilliant part. They don't just use it to scare predators. They use it as a flashlight. They release tiny clouds of glowing particles that drift for a moment. This creates a temporary backdrop that outlines hidden prey. Others shine faint glimmers across the seafloor so that reflective organisms stand out. Their eyes are tuned to these specific wavelengths. They are using their own light to carve meaning out of the dark. These shrimp demonstrate that vision can be an active process. They are painting their world with light so they can see it. We have climbed high to the very roof of the world. Some mountain goats have panoramic vision for cliffside navigation. High mountain cliffs present an unforgiving environment. A single misstep here could be disastrous. Yet, the mountain goat moves with the grace of a dancer. They rely on eyes positioned to provide a broad, sweeping view of the world. Their visual fields overlap in a way that reduces blind spots. They can track the position of a tiny ledge, a loose rock, and the horizon all at once. Their pupils are horizontal, and their retinas are arranged to have exceptional sensitivity to horizontal lines, the lines of the earth. Even while moving quickly across narrow ridges, they can detect subtle shifts in texture that indicate safe footing. Their visual system is not designed for reading books or spotting flowers. It is designed for stability. It is an anchor, keeping them safe on the edge of the sky. In the tropical night, eyes take on strange and beautiful shapes. Some animals have pupils that constrict into pinpoint stars. Certain species, such as cuttlefish in the ocean and geckos in the rainforest, possess pupils capable of forming intricate shapes. They appear as narrow slits, crescents, or even star-like patterns. These unusual configurations provide advantages that ordinary round pupils cannot. Star-shaped pupils can reduce chromatic blur. They help the animal judge distance more accurately in uneven environments by providing multiple depth cues simultaneously. When light levels shift, these pupils morph smoothly into new configurations. It is a biological kaleidoscope. These transformations are controlled by finely tuned muscles that respond quickly to the jungle light. To look into the eye of a gecko is to look into a different way of seeing a geometry of vision that is alien, yet perfect for its world. Let us go smaller than we have ever gone before, down to the level of atoms. The retina converts light into electricity through quantum-level events. Inside each photoreceptor in your eye, a single molecule waits. It is waiting to catch a photon. When that photon arrives, it triggers a transformation at the smallest scale of physical reality. The molecule changes shape. It twists. This process happens faster than almost any chemical reaction known in biology in femtoseconds. This tiny shift initiates a cascading series of biochemical events. It is like a domino falling. It amplifies that tiny signal until it becomes an electrical impulse strong enough to travel to your brain. The entire process depends on quantum interactions. Millions of these reactions occur every second as you look around the room. The transformation from photon to neural signal is the most elegant feat of the visual system. It turns the intangible nature of light into something your mind can hold. Think about what you are doing right now. You are reading. The eye learns to interpret letters and symbols through cultural wiring. Written language is a very recent development in human history. We did not evolve to read. Yet, your visual system adapts readily. It repurposes older neural pathways, areas originally used for recognizing natural shapes, like tracks on the ground or leaves on a tree. It shifts them to interpret letters, numbers, and symbols. Over time, repeated exposure strengthens these connections. As a child, you learn to associate shapes with sounds. Now, as an adult, the process is effortless. You do not see curves and lines. You see meaning. You hear a voice in your head. This is cultural wiring. It demonstrates the brain's incredible flexibility. The act of reading is a collaboration between ancient visual circuits and newly acquired patterns. You are hacking your own biology to share thoughts across time. And what is the most important thing those eyes see? Other people. Humans engaging with faces use unique visual pathways. When you look at a human face, specialized networks in your brain light up. These networks do not respond in the same way to objects, landscapes, or tools. They are just for faces. They rapidly evaluate subtle differences: the tilt of an eyebrow, the tension in a lip, the direction of a gaze. They operate with such efficiency that recognizing a familiar face requires only fractions of a moment. This system develops early in life. It supports empathy. It supports bonding. It allows us to understand each other without saying a word. To see a face is not merely an act of vision. It is an act of understanding. We have traveled from the bottom of the sea to the top of the mountains, from the quantum molecule to the spinning galaxy. Vision emerges from a dance between light and neural firing. Every moment of sight begins with the arrival of light, but it ends with you. Light itself carries no interpretation. It arrives as raw energy. It must be captured, organized, and transformed by countless cells within the eye and brain. Signals interact. They reinforce one another. They create a map. And then, consciousness steps in. Human eyes are gateways through which consciousness interprets reality. The eyes gather information, but meaning arises when the mind engages. You add memory, you add emotion, you add your history. Every scene you see is a fusion of the external world and your internal world. Consciousness selects what to focus on. It filters out the noise. It turns raw physics into a lived experience. The eye serves as the threshold. It is the doorway between the universe out there and the universe in here. Through this gateway, reality becomes something more than light and matter. It becomes a story, your story. As we come to the end of this quiet journey through the mysteries of the eye, I hope you feel a little more connected to the wonder woven into every moment of seeing. Even with closed eyelids, the mind carries its own soft glow. It is shaped by memories, colors, and gentle impressions that echo long after the light fades. You have just wandered through a world of tiny miracles. Each one happens in the space of a heartbeat. Each one reminds us that our senses hold far more depth and beauty than we often realize. If you enjoyed these peaceful explorations, remember that this world is always here, waiting for you to look closely. But for now, the looking is done. The learning is done. Let your breathing slow. Allow the day to fade away. Let yourself settle into comfort. Your eyes have done their work. It is time for them to rest. Good night.